what can we tell from these Lewis structures? That's the main concept of this thing called VESPR model. So VESPR, valence shell electron pair repulsion model. And it basically tells us the molecular shape, three-dimensional shape that these molecules take based on their Lewis structure. And we can mainly, and this is the main thing about it, is that the structure around a given atom is determined principally by minimizing the electron pair repulsions. So electron pairs like to repel other electron pairs, and they like to repel bonded electron pairs, especially. So the idea is these forces will shape the atom three-dimensionally, and it's important for us to understand how this works. Basically, they repel other things. All the electron pairs repel each other. And there's two ways of determining, or two ways of writing the configuration, and they're both different. The first is the molecular geometry, which is more relevant in our case, but it's harder because there's more terms. By more relevant, I mean it is the exact three-dimensional arrangement of the molecules in the atom. Of atoms in a molecule, I should say. Whoops. I didn't write that. The book did. Blame the book. Engage. They're going to sue me for this video. Anyway, so the arrangement of the atoms in the molecule. So this means water, like this, water is considered bent because the atoms of hydrogen around the oxygen are in a bent formation. That bentness, that bending, is formed because of the electron pairs that repel the bonded pairs. They actually push them down and make it a bent shape. Then you have, and we'll talk about that when we get to the chart, but there is the second one, which is called electron geometry. The electron geometry is the three-dimensional arrangement of electron pairs, and this corresponds to both bonding and non-bonding electron pairs. We look at them indiscriminately. So, for example, for water, it won't be bent anymore because water has technically 4 electron pairs. It has 2 that are bonded and 2 that are not bonded. This means, and we can consider all of them to be equals here. This kind of looks like Mickey Mouse, but whatever. So I have to finish it off. What does Mickey Mouse look like? It's not Mickey Mouse. Just put legs on. Close enough. So anyway, we have 4 electron pairs. These 4 electron pairs are considered equal. This means that the electron geometry of water is actually tetrahedral. Meanwhile, the molecular geometry is bent. So that's important to understand too, is that the electron and molecular geometries could be different because they account for different things. Molecular geometry accounts for what the lone pair of electrons, if there are any, do to the three-dimensional structure of the atoms in the molecule. Meanwhile, the electron geometry just counts the amount of electron pairs in the molecule around the central atom and uses that to determine the shape based on the electron clouds, on the number of electron clouds, when you consider that each electron pair is an electron cloud. So is there any questions on that before I continue? The 2 different types of geometries. One is the actual shape. The other is how many pairs of electrons are actually in the model. Nope. Okay. Moving on to, okay, so there are many different names, but they follow a pattern and are not too hard to remember, especially with the extra credit and the homework that I'm going to give you. So the first one is linear. So if you have an atom that has 2 electron groups that are both bonding to an atom, they form a linear pair, right? Because, for example, is CO2, BeCl2, CS2, where you have no lone pairs on the carbon and you just have 2 bonded things. This is linear for the molecular and the electron geometries because there's no electron pairs to repel anything. And the furthest part, so these electron groups, 1 electron group, 2 electron group, these electron groups are as far away from each other as possible. Something else that I want to mention is when we're doing electron geometry, we're talking about electron groups. Now, an electron group, there's this term called the steric number. So I'm going to write this down. We'll learn about it more next week, but I'll write this down. So number of electron groups. So the steric number is the number of electron groups. And what this means is that, what is an electron group? So an electron group is one of the following things: a lone pair, a single bond, a double bond, or a triple bond. Those are all electron groups. A triple bond is not 3 electron groups, it's just 1. Because all those electrons are going to one atom and they are in one direction. So there's 4 chances to have, there's 4 definitions of an electron group. Now, the steric number determines this, or the steric number is the sum of these electron groups. And that could be used to help us with our electron geometry. So electron groups corresponds to the steric number. So another way we can write this is steric number. Okay, so the steric number is 2, and both of those 2 are bonding. You're going to have linear for both your molecular and your electron geometry. So linear, that's the first one. Then let's increase our steric number to 3. And let's say they all bond, such as boron tetrachloride or boron trichloride, where there's no lone pairs. Your electron geometry, since there are 3 electron groups, will be trigonal planar. What that means is the 3 groups will be as far away from each other in a 3-dimensional plane as possible. And that degrees is 120. That's the furthest they can be away from each other, no matter how you look at it. That's trigonal planar. Then the next one, for same thing for molecular geometry, it'd also be trigonal planar because there's no lone pairs. Now we're going to introduce lone pairs. So let's take away one of these bonds, this BCl3, take away one of the bonds, replace it with a lone pair. That changes things. Here's how. Adding that lone pair will then push, just like we saw for water, will push the other paired or bonded electrons away from each other, or push them down away from the lone pair, and it will kind of squeeze them into a bent formation, just like we see in this picture right here. It'll push them down. Wherever you see lone pairs, it pushes the bonded atoms down. In this case, the molecular geometry will be bent because the shape of the molecule is bent. But the electron geometry will still be trigonal planar because there's 3 electron groups still. Even though one of them is now a lone pair, there are still 3 electron groups. And again, they are counted indiscriminately. So every time you have your electron geometry as trigonal planar, your steric number is 3. Every time it's tetrahedral, your steric number is 4. But the molecular geometry changes depending on what the lone pair electrons are doing. If that makes sense. Okay, I'll stop here. Any questions? And for the video, I cut out the questions, by the way, for most of them. So the ones I could find. So if you don't feel shy. No? Okay. All right. So next, steric number 4, meaning you have 4 electron groups in all these cases. The first easy one is when you have 4 electron groups and they're all bonds, such as methane. We've seen this one before, and this is called tetrahedral. So tetrahedral is a tetrahedron in 3 dimensions is something that in a 3-dimensional space, all 4 points are as far away as possible. And the angle is actually pretty important to know, 109.5. That is the key angle for tetrahedral. That it's important to know that one at least. And the other, and the simple ones, such as 120 and 180. I know that the bent is going to be less than 120. So that's that. Then when you take away one of these bonded ones and replace it with a lone pair, what happens? The same effect. These lone pairs are going to do the same thing every time. They're going to push down on the remaining bonded electrons. In this case, what's going to happen is it's going to push down on the 3 until it makes kind of like a tripod. And that's exactly what's going to happen. It's going to be called trigonal pyramidal, which in essence means bipod, or no, tripod. Whoops. Which means tripod. So trigonal pyramidal. But the electron geometry for all of these cases will still be tetrahedral because the electron groups remain the same, still 4. Then what can happen is we can take away another bonded pair and replace it with a lone pair. This will more greatly push the remaining bonded atoms together, making a bent structure again. But in this case, the bent structure will be forced more bent than we saw before because instead of one pair of electrons pushing them, there is now 2 pairs of electrons pushing them. So for water, this is water's case, it's very bent. If you compare the bentness of this one that I have circled up here and this one down here, this one's more bent. And the angle will be a lot less than 109.5. Okay, any questions on that? No? Okay. Next is steric number 5. So steric number 5, and then we only go up to steric number 6. And here's 5 and here's 6. Steric number 5, you have a lot of stuff going on. And we can do process of elimination. The first thing is when you have all 5 electron groups as bonded pairs. We call this trigonal bipyramidal. So it's kind of like a tripod with 2 tops. So imagine a tripod is a camera in the middle. That's trigonal pyramidal. Trigonal bipyramidal is if you have 2 of them and they're kind of like, well, like spread out like this. And you have the tripod. So that's trigonal bipyramidal. It actually has 2 angles, but don't worry about those angles too much. So the electron geometry would be trigonal bipyramidal for all of them. But as you increase the number of lone pair electron groups, the molecular geometry changes. So obviously when you have no lone pairs, it's going to be also trigonal bipyramidal. When you add a lone pair, you're going to get some pushing into a seesaw formation. Again, this one's not too important because you'll see it come up not much. So I will put an asterisk next to some that aren't going to come up too much. So seesaw, T-shaped, and square pyramidal. You don't really see that come up too much. And square planars, it's fair game. But yeah, the other ones you don't really see up too much. But okay, so that's a seesaw. Then if you take away another bonded, so now you have 4 bonded, take away another one and replace it with a lone pair, you now have 3 bonded and then 2 lone pairs. So it'll create a T-shaped arrangement. So imagine if you have water, but you have a 3rd atom bound. So you're going to have your 2 lone pairs at the top, and it will kind of push everything down. But if you have it in an arrangement that is like a tripod, it will cause too much of a problem. It'll be too close. So the best way is if it like rotates like a T. And then, but because it still has to be far away from the other one. So it would have to rotate 3-dimensionally and become like a T. So that's why they call it T-shaped. Like you kind of see here. So like, no, when you see here. So the electron pairs would be like one facing this way, like up, the other one facing back the other way. So it'd be like rotated. Okay, then the last one would be linear again. So how do we get linear? So the electron geometry again is a trigonal bipyramidal. We're replacing we're going from this one to this one. We're replacing the 3rd bonded electron, the 3rd bonded pair with a lone pair. So what that's going to do is it makes 3 lone pairs, which are going to act in a weird way. They're going to kind of act like a buffer system between the 2 fluorines, like airbags. So they're going to like kind of puff out around the xenon. And meanwhile, the fluorines will be on one on the top, one on the bottom. So kind of, instead of pushing them towards each other, it'll kind of even them out on the top and the bottom, or the left and the right, however you want to look at it. And the electrons will be like, one will be up this way, one will be this way, one will be this way. They'll all be in opposite arrangements, 120 degrees away from each other. And then you'll have the two atoms, the fluorines, will be pointing out. So that's why it's linear. It kind of like relinearizes itself when you add too many electron pairs, if that makes sense. Hopefully it does. I'm not sure. Okay. Next, and the last one, thank God, is octahedral. So octahedral, despite its name of being octa, which usually means 5, not 5, usually means 8. Is it? My numbers today are messed up, which usually means 8. Octahedral actually means 6 now. Why? I don't know. So the steric number of 6, meaning there's 6 electron groups. The first one we can talk about is pretty easy, where the molecular geometry is also octahedral, and that is CF6, great example, where all 6 of them are equally arranged in 3-dimensional space, and the degree is 90 degrees in between each one. Then what happens if we remove one of them and replace it with a lone pair? You get square pyramidal, which means basically like a normal pyramid. You have a square bottom, like the pyramids in Egypt, right? Square bottom, and you have like a thing at the top, like a point at the top. That's basically what a square pyramidal is going to look like. And the lone pair of electrons will kind of dictate, will push the 4 corners of the pyramid down, and then the other one will be like to the side, kind of. Yeah, it'd be weird, but yeah, you get the point. Okay, and then the last one is, the last one on the bottom is when you have replace another one of those bonded electron pairs with another lone pair to get xenon tetrafluoride. That's another one. So what will happen here is we have a square planar. In reality, so you're having those 2 electron pairs. They're like opposites like this. They're like kind of pointed away from each other. And they are going to be pushing all of the 4 bonded atoms downward, making a square pyramid. Or sorry, making a square plane. Wait, it's square planar. Oh, my bad. So what's going to happen is, sorry, they're actually going to be opposites. So that didn't make any sense. Let me rephrase that. The lone pairs are going to be opposite of each other. Kind of like I knew I was getting at something. Kind of like we saw for this case, where we had linear here, kind of relinearized. You had the electrons in the middle. Same thing is going to happen here, where you have the electrons, the 2 lone electron pairs are going to be in the middle. And it will kind of act as a buffer and keep all of the other 4 bonded pairs in a planar arrangement, in a 2-dimensional planar arrangement, as opposed to bending and being 3 dimensions. That's how that works. Yeah. Okay. So that is it for going over these shapes. This is one of the main parts of chapter 11. The other parts that we're going to learn are having to do with molecular orbital theory, kind of getting back to the electrons, but into this kind of too. And then hybridization, which is hybridized orbitals, and other things like that. So are there any questions on this? I'll end the video.